Hi, today we will be presenting our group assignment for the Signal and System course related on linear time invariant system. So we are from section 7, group 5. My name is Gary and my teammate is Cheng Hok. So I'll be explaining the task 1. So for task 1, we're given these two signals and we have 3 tasks. First is to generate these two signals in the MATLAB. Second is to add these two signals using Fourier transform. And the third task is to evaluate the convolution result using Laplace transform. So for task 1, so for region 1, when time from 0 to 1, it is a +2 slope. From 1 to 2 is a -2 slope. So this is the unit step function for x1, and the equivalent is a triangular function, as you can see, 2 try t minus 1. And for the second signal, x2, it is a rectangular pulse from -1 to 1. So this will be the unit step function, ut plus 1 minus ut minus 1, and its equivalent is rect t over 2. So this will be the MATLAB code for task 1. We clear and close. We'll clear and close first, then setting a time exit from -3 to 4 seconds. So for the first signal, from what I've mentioned above, 0 to 1 will be +2 slope. At time from 1 to 2 will be -2 slope. Then second signal, x2, is from -1 to 1 with a 1 amplitude. So plotting, this is to plot the graph, and as you can see, the resulting waveform is exactly as what we needed above, a triangular signal from 0 to 2 and a rectangular signal from -1 to 1 with 1 amplitude. So for the second task is the addition of signals. Using this property, the linearity property, addition in time domain can be also done in frequency domain. So for the first signal x1, using Fourier transform, it will be 2 sin square e power to -j omega, and the second signal, rectangular signal, will be 2 sin omega. So the addition of these two signals will result to this z omega equation. And the continued MATLAB code for task 2 is, this one is the addition, direct addition. We directly add the two signals in time domain, and this is the result. This code here is to convert the signals to frequency domain using FFT, and sum it up goes to Z frequency. And then we have to convert back to time domain using IFFT. After plotting, so this figure shows that both of the waveforms are the same, proving a accurate analysis. Moving on to third task. So the convolution theorem states that yt, the multiplication in time domain, is also can be done in the S domain. So we will Laplace transform x1 and x2 into their equivalent form in S domain. Then we multiply it. So we will multiply it in Laplace domain. So ys will be in this equation. In order to get back the yt, we have to inverse the ys to get yt, and this will be the final result of yt using inverse Laplace transform. So MATLAB code for the third task will be this. Define a unit step function first, then y calculator is the equation derived from the inverse Laplace transform, this one, and y numerical is the convolution directly using x1 and x2. So following by the plotting of the result, so the green circles are the Laplace property result, and the one in red is the convolution result, and it shows two identical waveforms. They have the same shape, and hence proving the convolution theorem. Now I will pass to my teammate Chang Hao on task 2.
Okay, so here is my turn. I'm Chang Hao, so I'm going to explain about the task 2 here. So for task 2, we're going to it has 3 sub questions here. So first we are going to generate these 2 signal in MATLAB, and then we are going to perform the addition between 2 signal and verify it using MATLAB. And then lastly, we're going Fourier transform, and then we are doing the convolution and also verify using MATLAB. So firstly, we're going to look what is the mathematical expression of these 2 signal. So for this for this triangle shape signal is GT. So GT, we write it as t plus 1 times u plus t and minus u t minus 1. And then for this one, this is the HT. So it has 2 rectangular signal. So we're doing it like this, like it's start from -1 to 0, so it's +1 minus ut, and then it start from 1 ends at 2, so it's -1 minus 2. So this is the code for us to generate these 2 signal inside the MATLAB. So first you can see we define the G first, and then we define the H, and then we plot it. So this is the plotting, this is the generated signal in the MATLAB. And then secondly, we are doing for Laplace transform of GT and HT. So, and actually we are just going to find ZT and find the ZT, and ZT is the addition of these both signal, but by using a Laplace transform, it's easier for us to perform the addition between 2 signal. So you can see after we expand the GT signal is doing this after expanded, and then so it's easier for us to do the Laplace transform here, and then here is the answer of Laplace transform. And also we are doing the same thing on HT here, and we expand it, and then we just transform it using Laplace transform. So we can just plus it, and plus it. This is the answer of Laplace transform. And then since the question is told us to find ZT, so we are going to transform it back to the period, back to the time. So this is the answer. So we transform it unit per unit. So this is the answer of it is ZT equals to t plus 1 u t plus 1 plus 2u t plus 1 minus 2ut minus u t plus 1 minus t minus 1 u t minus 1 and minus u t plus t minus 2. And this is the verification using MATLAB, and as you can see, for the red line it is our calculation, and for the circle dot there it is the verification using the MATLAB, and this completely overlap, so which means our calculation is correct. And then here is the code for us to generate this graph. As you can see, we perform the addition here, and then the plotting. Okay, so here is our Fourier transform. So firstly, we're going to find GT and HT first. So for GT, we're writing it in another way since it's easier for us to do the Fourier transform. So since if you write in that way, we can't really use the table to directly transform it. So we use the integration method to transform it, and here is our final answer. And then for h omega, right, it is rectangular. This rectangular function, so we can just directly transform it using this using the table. And here is the result for y omega, because it is a convolution, so we can just directly multiply it for each other. And then for this is the MATLAB result. As you can see, the numerical convolution using MATLAB and our theoretical result is completely overlapped, so which means our calculation is correct. And since we have right inside the code where our multiplication in frequency domain, it will correspond to convolution in time. So that's why the plot is that's why we can see the plot for YT. And that's all from me. Thank you.